Hi, everyone. Thank you so much for joining us this afternoon. This is the another in the RISS community series. We have the pleasure of speaking today and learning about the research of Dr. Jean O. She's going to talk about her research and work in social robot navigation. And Jean has been an important part of the Robotics Institute for a number of years, and she'll get to share her journey with you and where she's really focusing her research to have an impact on quality of life and on the future robotics. So today we'll have the question and answer is done through meeting calls. I'm going to drop that link in both of the chat, so you have that, and you'll have the opportunity to ask questions in there, and you can also upvote questions because a lot of times there'll be some similar threads that we'll want to explore together. So again, this is a special talk to help you explore ideas in robotics and think about engaging in the future in robotics research and STEM careers. So I want to welcome Dr. Jean O and thank her for joining us today and for her talk with us. Thank you, Jean.
Thank you, Rachel, for the introduction. So, hi, everyone. My name is Jean, and let me just start. Oops. Okay. So before I talk about the social robot navigation, let me introduce my research group, Robot Intelligence Group. So we do research on social robot navigation, which will be the main topic of today's talk. And also, we also work on semantic understanding for robot intelligence, so a lot of language-related research as well. So in this video, the one student is actually commanding the robot to manipulate some objects using natural language. So I'm going to stop this video. This you that I'm excited. So it's about the creativity. So creativity is very is what a lot of machine learning and I developed our area that used to be human only. So how can we make the AI system more creative and also facilitate human creativity? We simulation environment to help making better decisions. So it is actually linked to the social robot navigation research that I'm going to talk about. So if time allows, I'm going to discuss a little bit about this part as well. And then this is the current members of our group. So I just highlighted some of the students who used to be the RISS scholar and also the current RISS scholars this year. So Ingrid, Abby, and Bev were RISS scholars in the previous years, and they joined our group to do the research. And then Jishuan and Shonak and Jansin are the current year. So I'm very excited. All right, so for the social robot navigation topic, so this is kind of the overview, but we can more discussion on how much time we have. So I'm going to go through sort of a taxonomy problem. So the what kind of problem is in, and among them, I'm going to use 3 example algorithms to illustrate this problem domain and what the state-of-the-art research is in this domain. And then a little bit of a the current work that has to do with this simulation idea that I mentioned, and then what can be done in the future, because there's a lot of remaining work to be done to solve the real problem. Okay. So let me start with just a general robot navigation problem in the real world. So if we look at this example, this is kind of a realistic environment to a little bit of extreme difficulty navigation. And in this environment, if we just look at the scene, we see a lot of static obstacles that are there, not really moving, but it's good. How to and then also there are a lot of moving obstacles, dynamic obstacles, including pedestrians, bikers, cyclists, and so on. And then also if we look at this scene for a little bit, there is a invisible guideline. So there are the rules. So good examples are traffic rules. So they are not really visible, but they define the members of the society. So some more, better like formally defined as the rules, and sometimes it's just the norms. So the members of the society certain kind of ill-defined rules. So the just formally defining the problem, the general navigation problem, very generic, given a destination, sometimes called a goal. The task is to face of motion actions to move from the robot's or the agent's initial state or the current state to it is finding the sequence of actions to solve the problem to reach the destination or goal. So the common objective used navigation is mostly focused on the actual reaching behavior. So there's a destination, so the robot needs to figure out what is the shortest path, for instance, or fastest route. This is similar to whenever you use a map service phone to go somewhere. It finds a path that is taking the shortest time or this path, the length. Okay, and then at the same time, the safety, which is collision avoidance, is a default okay. And then the human aware navigation. So that's where this social comes from. So the social robot navigation includes additional in addition to the intention to reach the goal without collision, there is added part. So it is a notion comfort. So comfort is just a little bit more than just the safety. So avoid a collision by more margin, it is still considered safe, even if it was very close, but it will generate discomfort. So that's the difference between safety and comfort. And the other one is the naturalness. So because the robot is operating in a human environment, there is a expectation. Maybe even if it's a robot, maybe they have to behave in a human acceptable way. Maybe not necessarily mimicking the human behavior, but it has to be natural enough so it's not really disturbing the rest of the population. Okay. So given that, so under this social robot navigation, this is kind of a rough grouping of existing work. So the navigation, the most generic form is the first one. So as I mentioned, the main objective is reaching the destination. And then the social objective in this case would be the safety, so avoid collision. And in the general autonomous navigation, actually the environmental context or the physical constraint to avoid a collision is very, very important. So computing the right level of traversability is one of the core research area for navigation itself. And then the second category is a pedestrian prediction. So this is not a navigation algorithm. So it is more of an observation of the agents in the same environment and try to predict where each pedestrian is heading, so that maybe use that information to plan better or do something. So it is kind of a sub-problem under this category because it is analyzing dynamic scene. But as you can see, there is no goal in this problem definition. So it is just predicting where people are going, but the robot or the observer or the agent doesn't necessarily have a specific goal here. So if we use this algorithm on a robot, for instance, it can be just wandering around among these human pedestrians without really disturbing, but it's not really going anywhere. It's just wandering algorithm. Okay, and in this category, the social objective naturally becomes the naturalness, because we care about how well the robot or the agent kind of blend in this population. And surprisingly, the environmental context is somewhat ignored in this both pedestrian prediction and the social navigation research work. So the reason probably is it is already very difficult by just introducing dynamic agents to avoid. So the problem was simplified in these two problem formulation, as if the environment is free of static obstacles. So, and also the terrain is pretty flat, so there is no difficulty traversing. But the real challenge, the main challenge in these two categories is more to do with how to avoid dynamic agents or dynamic obstacles. Okay. So if anyone's interested in including both static and dynamic obstacles, that's a very good area of future research. Okay, so as I mentioned, the pedestrian prediction was not a the navigation algorithm, whereas the social navigation is the navigation algorithm that considers dynamic obstacles in the environment. So the goal-oriented objective here is still the same as the original navigation. So the agent has a specific goal or destination to reach. And then the social objective in this case is actually combining all of these. So it has to be safe, collision-free, and then also because the robot is navigating in human environment, it should be it should assure the comfort and naturalness. And at the same time, the environmental context is going to be important for social navigation, but so far there are very few existing work that's doing both. So again, this is a very good future direction that's still left open. Okay. So that was kind of an overview of the field, and I'm going to start explaining a little more detail on the pedestrian prediction part. So in fact, under this pedestrian prediction task, there has been a lot of interesting research came out in the recent years. So there are many good approaches. Even before deep learning approaches, there were like more probabilistic approaches, and now more deep learning based approaches. But again, the difference here is these pedestrian prediction algorithms are not for navigation planning. But the reason that reason why we study these prediction algorithms is because they are still very useful to model the interaction between these dynamic agents. So it could serve as a partial or a subcomponent for the navigation algorithm, for instance. Okay, so I'm going to use social attention, one of the prediction algorithm, to explain the problem. So this was a work done by one of my students, Anirudh Vemula. So here the basic assumption for this social attention approach was people tend to, maybe not everyone in the same environment, but focus on maybe a small subset of agents when they navigate in a crowd. But that subset may not be the ones that are closest. So that was the assumption. And then to illustrate the problem, so let's use this simple example of 4 people in this case. So the edges kind of represent the relationship between the agents. So if this agent in the center is the robot who's making the decision, then the agent will consider these other 3 agents in their decision making. So because the decision will, or the results will depend on how the other agents also move in the same environment. Okay, so this is at a fixed time step. Then there is a spatial relationship between agents at a fixed time step. And then if we unroll like one more time step, then between time step t and the next time step t+1, we can see the temporal dependence. So this is the same agent. So that agent, this agent was here at time t, but at time t+1, maybe at a different location. So what is the relationship between itself at a previous time step and the current time step? So this represents the temporal dependence. Okay. So that was a kind of a example illustrating the problem. And now we are moving to a computational representation for the same information. So if we use something like a graph, then each node can represent an agent. So in this case, we include the 3 agents, 3 nodes, each representing a single agent. And then the blue edges here represent the spatial edge at the fixed time step, the relationship between 2 different agents. Okay, and then the green arrow, green edge represents the temporal dependence. So at the next time step, this human one may be at a different location. So how to represent that part? Okay, so if we unroll this graph, then you can see kind of very similar representation as the previous illustration. So the 3 agents at time step t, and then at the next time step at a different location. So here, again, the node represents each agent, and then the green arrow, green edges captures the dynamics between the temporal time steps, and then the blue ones represent the spatial relationship between 2 different agents. Okay. So hopefully so far it is pretty clear. But anyway, if anyone has questions, please feel free to ask. Okay, all right. So that was a conceptual representation. It is a very abstract representation. And now we have to choose a model to actually implement this idea. So spatial temporal graph is a very classical idea that has been used for many other things, and there were different computational implementation. And nowadays, people use neural net a lot. So, in fact, for instance, convolutional neural net and recurrent neural net, we can choose between different models. And intuitively, because the RNN tend to do very well representing sequential data, something like languages, it was the popular choice at the beginning. So, okay, so just a quick recap of how we might use a CNN or RNN to process the sequential data. So for we can actually use a CNN too. It's a one-dimensional CNN, and then in this case, the output is a function of neighboring input. So you can, this kind of illustrates how we compute the output if we get to use 1D CNN. And then on the other hand, in the RNN sense, it's recurring function. So we reuse the output from the previous time step and then the current input. Okay, so we will first look at the RNN-based approach. So recall that spatial temporal graph. So this structural RNN is a neural network version of that spatial temporal graph. So this was proposed by someone in so the problem domain is different, but you can we can see there is a person's movement, so that represents the temporal dependence, and then the spatial edges here represent the relationship between an agent, in this case a person, and the objects in the same environment. So this problem was used for representing a person manipulating objects in the environment. Okay, and then we can see instead of using objects here, we can put other agents because it can well represent the spatial and also temporal dependence. So that's how we did it for the social attention idea. So the network structure is pretty much similar to this structured RNN, but it was done for the trajectory space instead of like object location. And then the core idea, the main idea for this social attention was this attention module. So we will quickly visit what attention module is. So attention is a just another neural net function that is kind of reorganizing the input space. If we can rephrase this, okay. So when the inputs are given, we want to kind of generalize that input into some sort of a context, so that it can be you can put some weight, so that we know like which part of the input is more important in making decisions and so on. All right, so I'll just quickly go through this part, because so for the attention part, we have two options. So we can either use a soft attention, which is the softmax over all these context vectors. So in that case, it will be a kind of smoothed out version. So it's a great choice for the backpropagation. But if you get to use the hard attention, which is just picking just one best match, then you might also use a sampling method so to mimic this smoothed version. So for using this attention idea, so going back to this trajectory prediction, here the context is representing the social impact. So one agent is making decision where there are many other pedestrians kind of moving around. So among these other pedestrians, this attention mechanism is choosing whom to pay attention. So it is assigning like who's going to affect the agent's decision making the most. Okay. So it turned out to be a good choice. So it matches with our initial hypothesis. So when people move, people tend to attend to a small subset of the agents in the environment, but not necessarily the closest neighborhood. So the background information is the previous approaches, the previous state of the art was kind of sharing the same idea, but they only look at the closest neighbors. And what we found out was it's not always the closest one. So I have some examples to show what that means. So if we look at this example, so this red one is the agent who's making the decision, and the blue circle shows the amount of attention distributed. So in this example, it just shows when you're far away, you still want to keep most of them in your attention zone just in case. So it's well distributed. And then in this other example, what it's showing is the counterexample of closest neighbor versus whoever is moving faster or has a larger chance to get closer. So in this case, this green agent and these two are the closest one, but especially this one has a very small size attention, which means since this agent is not really moving much, this agent is not going to pay too much attention to this one. Instead, because this agent is moving closer, more attention will be paid here. So that was an example of using RNN to represent this idea. And then now we are going to look at one example of using CNN, which is a newer trend. So the intuition here for preferring CNN was RNN results. It works well for representing sequential data, but it tends to get noisier as the length of the prediction gets longer. So in order to do better for the long-term prediction, maybe CNN is a better option. So that was the initial hypothesis, and it turned out to be the case. So there were our paper also, our results also confirmed that, and then there were a couple of other papers also had a similar results. So. Okay, so this algorithm was developed by Eagle Zhao, who recently graduated. So I'm going to kind of show a little bit of a detailed version of this algorithm. So, okay, so the basic idea here is based on this assumption that whatever we do, our motions will be affected by other people's motions. And also the second assumption is there are kind of tendencies that are being repeated. So what Eagle proposed was something called the motion patterns, which are kind of capturing these repeated patterns in this trajectory space. So in this example, these two, even if they are not exactly the same, probably they'll have a similar effect on the blue agent's decision making. Okay. So this is a kind of a simplified example to illustrate what we mean by motion pattern. So in this example, these arrows represent a motion pattern. So in this case, there are 12 motion patterns supposedly learned. Then if we observe this green trajectory pattern, then what we want to do is using these motion patterns can we represent this green trajectory using the learned patterns. So in this case, it is just the numbers represent this motion pattern matches very well. So it has a high value with this observation. And this one also has a relatively high value because but the other, on the other end, they have very, very tiny probability of being similar to these observations. Okay, so quite intuitive. Okay, so in order to implement this as a convolutional neural net, what Eagle also did was coming up with the new convolution operator. So the reason for that is convolution, the traditional classical convolution operator is computing the correlation, which is not the best fit for our purposes. So in this example, it illustrates the drawback of using correlation as a convolution operator. So in this case, given this observation, the pattern, we want to choose this one as the closest one. But if we use a correlation, then this other one comes as the closest match. So instead of using this, we define the new one that is more similar to Euclidean based convolutional. Okay, and then the second thing that we did was representing the uncertainty in the prediction space. So the previous existing approaches were just predicting one trajectory. So it is more of a deterministic choice, single peak model. And here, if we use just this regular Gaussian distribution, it will do the same thing, just showing one possibility. And what we did was using the mixture model so that it can present alternatives. So in this case, the agent has actually two different options to avoid this collision with this observation. So these are possible predictions. So it has more flexibility in the prediction result. Okay. And then the architecture is designed, so this upper part represents the agent's own trajectory. So it is encoded into its own history. And then the rest, these are the other agent's trajectories. So this corresponds to the context in the other social attention model. Also had this social impact. So this part is all encoded into the context trajectory. And then do the social pooling. So this part is somewhat similar to the other trajectory prediction. Okay, and then as mentioned, the output is using the Gaussian mixture model, so it can have a multimodal output. Okay, and then this part shows the seeding of the initialization. So the motion patterns are learned from the data, but it starts with some seed motion patterns. So the results are showing the seeding is not really, the results, the learned patterns are not really sensitive to the initial seeding. So we tried with various different settings and then end up with the very similar learned patterns. So it was good. And then this part shows some output. So what happened and how we use the learned pattern in making the prediction. Okay, so the observations are represented using the learned patterns, and then it's used to make the predictions for the next steps. Okay, and more qualitative results. So here, what you need to look at here is the difference between these two dotted lines. So the circled one is the the truth, and then the starred ones are the prediction, and you can see how close they are. So that means the predictions are really matching very well with the ground truth. And there are a few cases that the two diverges, but even in those cases, you can see it kind of makes sense. Like for instance, in this example, there are like multiple stretching out, but the highest probability one is going straight. So it's based on the observation, which was just going straight, it is very likely prediction. So it is a explainable. Okay. All right. So there are a lot of existing work on this trajectory prediction, but the issue is what we are observing in this research community is we are somewhat trapped in the kind of the test bed that we have been using. So the performance is kind of reaching saturation, meaning that many algorithms are performing similarly. I mean, one is a little bit better than the other, but only in this evaluation setup. So I think it's time to think about how to change this evaluation paradigm for making the real progress. So that's a kind of future direction I hope I have time to talk about a little bit. Okay. And then how am I doing with the time? Okay, I think we still have time. So, okay, so we looked at the pedestrian prediction problem. And then now we are going to look at the navigation problem. So again, the difference is the navigation algorithm includes a destination, the goal. So given these pedestrian interaction prediction results, how can the robot use that information to reach its own destination? So, okay. So under this navigation, social navigation domain, roughly, there are three different approaches that have been tried. So the first one is inverse reinforcement learning. So this category is a somewhat supervised version. So you can think it as learning from human demonstration. So try to learn how human pedestrians navigate in a crowd and then try to mimic that kind of behavior. So the objective becomes the naturalness, like how human-like, how similar to how people navigate. Okay, so in this case, if we just focus on the naturalness, what happens is it can ignore hazard. So because there's no notion of a collision. So try to mimic the behavior, but no one is enforcing that you need to avoid the collision. So all the models just trained using inverse reinforcement learning will get into collision more and more if the scene becomes more denser. Okay, and then the other extreme is the forward reinforcement learning. So in this case, the reward to be defined, and usually the reward function includes collision avoidance. So if the collision, then there is a penalty. So that way, all the algorithms that's using the RL approach to much better having the safety guarantee almost, and also comfort, because you can set the comfort distance. So if the agents are too close or closer than 30 centimeters, then you penalize. So it can be enforced, but at the same time, it loses the naturalness because it's only focusing on the safety and like following the rules kind. So the behavior, if we just look at the simulated demos, you can tell who's who because of their kind of particular behavior. Okay. So what we did was let's take both So can we come up with an idea that can guarantee safety, but at the same time have some naturalness in the behavior? So the generative approach was the one that we proposed. Okay, so this algorithm is called the Navigen. It's a generative model, and how this was designed was kind of modularized way. So there is a part that's kind of computing the intention of reaching the goal. So it's a self-interested objective. So there is a goal to reach. So it plans for that goal. At the same time, there is this public or global objective of following the social norms. So you have to yield a little bit sometimes. Okay. And then this fluctuation is added for the natural kind of stochasticity. All right. And the idea, we didn't like invent this the idea of this self-interest and public interest and so on. This actually follows some theory called the social force model. So the social force model explains how human pedestrian makes the decision in the crowd. So the formulation includes the intention force, social force, and obstacle force, and fluctuation. So in this, sorry. So in here, we kind of omitted the static obstacle part because all the data sets don't even include the static obstacles, but this is the part that we need to include in the future. Okay. And so I'll kind of quickly go over this part because I want to leave at least 10 minutes for the question part. So the intention force is trained using something called the final displacement error. So there are two types of displacement error. So when we compare the trajectory or the planned trajectory with the ground truth answer, there are two types of differences we can use. So one is whether they, how different when they finished. So at the final location, are they at the actual goal or somewhere else? So final displacement error is measuring the difference at the final stage. Okay, so for the intention force, using this as a training loss makes perfect sense because intention force only cares about whether you reach the goal or not. Okay, and then the social force, on the other hand, is using the average displacement error. So this is the average displacement error is again comparing the two trajectories, and it is averaging out the entire sequence and take the average. So this is again, it makes sense to use this as the loss for training social force, because social force determines the actual behavior throughout. Okay. All right. And then the last thing we added was this resistance loss. So this was not part of the social force theory, but it was added to ensure the safety. Because as I mentioned, if we don't include this, then what can happen is there is no enforcement that can guarantee collision avoidance. So this was added. So the idea is similar to the reinforcement learning training. So there has to be some penalty if the agent violates this safety constraint. And again, this safety distance, it changes. This is a kind of social context thing that has to be trained from wherever the agent is. So an example we use is prior to COVID-19, it was 20 centimeters. And now everyone has to be 2 meters at least far apart. Okay. Okay, so this is a kind of the network version of the same architecture. So And then this example kind of shows the difference between just using intention force only and using both intention and social force. So it's a little bit hard to see, but here the red dots are the predicted part. And here you can see how close these red ones are to this other blue one. So let's just look at it one more time. So the red one getting very close to these next ones. So it is still safe, but it was fairly close. And look at this one. This is exactly the same sequence, but here the red one slows down so that the other agent to pass first. So look at it again. Here, agent slowing down so that this blue one passes by, so that it goes next. So, okay. So we also did the physical robot experiment and then got some good results. But evaluation in this problem is again an issue. So we keep seeing this issue with the evaluation. So right now, what we are currently working on is, can we do a better evaluation for the whole navigation paradigm? So in order to test with the human pedestrian, you have to run like real robot experiment and recruit people and then collect data, which is very, very time consuming and expensive and also subjective. So it's not very practical, also for the development purpose as well. So what we have been doing is, can we actually develop a simulator that we can kind of tune to generate very different scenarios? So we first came up with a larger set of evaluation metrics. So the typical metric that's used right now are those two displacement errors, which has obvious limitations. So we include a lot more different types of evaluation metrics to measure the performance. So this work was done by Advait and also Sam. And then first thing that we did was we collected all these new statistics from the existing human data sets. And then the finding is, and not surprisingly, they look all different. So this is a good thing to know, because this indicates that there is no such thing called one human behavior that fits all environment. So wherever the robot is deployed, the robot has to kind of learn to adapt to the new environment and new social norm. So this was matching with our expectation. And then also we tried to compare each of these top algorithms with the human behavior, like each data set. And then again, the finding is there is no single algorithm that is a clear winner. It's another expected result. So what we are kind of trying to do is how to come up with a mixture of these agent populations with the multiple different algorithms that will be able to mimic each specific environment. So that's what we are going to do. And then we have been doing a lot of like interesting experiments using the simulation environment. So like comparing how these performance degrades if the population becomes very, very dense. And it's interesting thing is this linear model is the most rude one. It's also called the blind agent. It doesn't really look at other agents. So it just goes straight to their goal. So they always reach their destination first because they don't care, they just go. And they end up in a lot of collision, but they still make it. So it is not surprising that's how it works, but these yielding agents like or polite agents, they never reach their destination because they have to yield and they need to avoid the collisions, so they take longer time, but the number of collision is low, so it is safe but never make it. So it is a kind of two different extreme. Okay, so we do a lot of algorithmic tournament. So hopefully we will get some interesting results from this type of algorithm comparison in a very different way. Okay. Okay. All right, and then quickly, so this the social navigation simulation environment and the algorithm toolkit. So we currently include 9 to 10 different algorithms, or re-implemented and integrated with the simulation environment. So we are going to release this soon for other people to also conduct research using this. So it will be exciting. Okay. And then the future direction is, again, the evaluation part is like our main interest right now. So we want to do more on this part. And then there's a whole lot of different issues to be included in this problem domain. So we recently wrote this survey article called The Core Challenges of Social Robot Navigation. And this includes all these different challenges, current, existing work, but more for the core for future research directions. So if anyone's interested, I recommend reading this article. Okay, and here are some references, and that's pretty much it. So hopefully, yeah, some people find the topic interesting, and if anyone has questions.
Wonderful. Thank you so much, Jean. I'm going to help facilitate the questions. And so several came in. I'm going to read them off and also invite anyone in the link. I'll put that link again into the chat. And you are welcome to upvote questions and ask additional questions as well. So Jean, one of the first questions was, how would different types of environments affect the human motion predictions? For example, do obstacles or really dense crowds have any effect?
The obstacles in the environment, yeah, definitely. So the density is one dimension that we play with a lot. So if there are only one other pedestrian, then the interesting thing is, if there's only one, then the robot has to be careful not to get too close. It has to be even farther apart, because a robot can be very creepy by like walking right next to one other stranger who's on the street. So that's a kind of very different behavior than in a kind of arbitrary crowd. And one thing we also noticed that is some algorithms that has never been trained on an empty environment. So when we launched that algorithm, the agent was confused. It was never left alone. So it was just kind of standing and just waiting. So yeah, but the environmental context, is it right now they're studied by a completely separate community. So they analyze the terrain types and where the static obstacles are and how to avoid them. But these dynamic obstacles are kind of treated as a separate thing. So I don't know if that was the question, whether the static environment will have an impact. It definitely will. And one of the current project is actually mandated. Like we have to deal with these static obstacles because it's in. So the example I used mostly are ground vehicles, but this other project is for the airplanes. Mm-hmm. An airplane landing at an airport. So there is always an airport and a fixed destinations. So the environment will be a significant part of the decision making.
Okay. Another question was, I know the focus was on how machines can get information and predict a pathway based on outside information. But is there a way that machines can communicate with the outside world to display the calculated route to pedestrians or other machines? So is there a way that a machine can communicate with the outside world to display the calculated route to pedestrians or other machines?
Yeah, that's an excellent question. So there are some research for the robot to actually show where the robot is going. So like showing the like the laser pointer, or kind of showing, displaying the arrow. So it is a interpretable behavior. So some people work on, especially people from HRI, human robot interaction, they are very interested in explainable behavior, interpretable, and transparency. So the robot, whatever it's doing, people just look at it and understand where the robot is going. But for other people, we just know or have a way to interpret other people's behavior, but robot is something else. So unless the behavior is very human-like, there's always a tendency to avoid. So when we, it's a kind of different story, but when we ran the real robot experiment, the results were very good. And partly the reason is people are more adaptive. So they do a really good job with navigating with the robot in their environment. So there is no collision, they look very smooth, but like robot does some part, but it's also partly human adaptation skill. So, but if the robot can actually explain where they're going and showing their path, I think that would be great. And also using speech. So like saying, excuse me, if it's like packed environment, or the algorithm fails if the density reaches to a certain extent, because there's no free space. So I mean, just sit here. But if we put a human agent, human can like go through even the like very, very packed environment by asking them to move away. So it is a way to take actions for other people. So like how to use your communication skill to move the parts that you don't have control over, but you can still ask. So that's a very human thing. But how can we utilize that in this navigation?
Okay, there's a couple more questions, and we also want to we only have a few minutes before we're wrapping up here, so I'm going to dive into that. How does RNN help in robot navigation? Could you talk a little bit more about that?
The RNN helping the robot navigation. So the RNN's job is to make future predictions. So given the observation, so you can observe the past trajectory and think it as a sequence of input. So like XY location, and then the RNN can generate the next XY's. So then you have a prediction of the future trajectory. Then in the future time step, you kind of have the or the predicted trajectories, and then the robot's future is also part of that. So that the part that I didn't really fully cover was the joint model versus like independent model. So that is the more older approaches were more reactive, which means you just observe other people and then try to predict where each of these other agents will be. And based on that prediction, I choose my best move. So it is a reaction to the predicted trajectories. But then the problem here is they also react to my action. So it becomes like, if I do this, you will do this, and then like it's going into this infinite loop. So the more recent models are doing the joint prediction. So making the prediction, including the robot itself. So when you're kind of computing this, the prediction, the robot predicted future, past and future trajectories are part of the whole prediction algorithm. So.
Wonderful. So we have 1 minute. We want to ask 2 questions in that minute. So and then we'll wrap up. So I'll speak very quickly. One is a technical, and then the second is going to really ask for your guidance. So the last technical one, in your experiments, did robot perception, uncertainty, or failure have any effect on your results?
Oh, yes, yes. Perception. So right now, yeah, that's another excellent question, because right now our assumption is the pedestrian tracking works fairly well. And to some extent that is true with the distance sensor. Tracking moving pedestrians are not that difficult these days, so we can get pretty good prediction of the tracking result. But if that part doesn't work, then the rest is not going to work. So, so perception is important.
Okay, we're right at 2 o'clock. Jean, would you share with us some last thoughts on the students that are here in the room and those that we're streaming with as well? Many of them are considering careers in robotics or future education in robotics, and they're trying to plan their next steps. And many of them are undergraduates. Do you have when you're working with undergraduates and you're trying to help them really plan different paths forward in their career and education, would you share some thoughts with us about what's important and what you would say or what you are saying to your current scholars right now?
Yeah, that's a difficult question. So take my answer with a grain of salt, or with some filter. So this is my personal thought. So with the kind of granularity. So if you are a little bit unsure, you generally like robotics, computers, but you're not really sure what you specifically interested in, then my suggestion is do a lot of math. So study math and have a solid math background. Then you can do anything. Like you can do really anything. Math is the underlying cornerstone. So that would be super important. And the second thing, like you kind of know what you want to do, then do a deep dive and you go for it. These days, a lot of information and also courses, talks, a lot of learning materials are online. So you can maybe do some self-study. And also if your school provides courses, take them and start doing some research or do some projects. So doing some hands-on experience will at least let you know that whether you will like it or not. So like a solid basic skill, since you're undergrad students, like the math and like programming skills. So those like basic skills would be useful for like whatever you do afterwards. So.
And this has been wonderful to have this time together today. I really appreciate you sharing the work of the lab and what you have created and driven and accomplished. And I know that we appreciated the time and getting this opportunity to connect with you. So I want to thank you again for sharing with us today. And we look forward to following up and to more scholars from around the world connecting with you. And thank you for your leadership and your engagement and your mentoring for all of us.